COCONUT-SVSM. My name is Jörg Rödel and I'm the initiator and maintainer of the COCONUT-SVSM project. This session is divided into 4 parts. It will start with an introduction and overview of the project by me. Part 2 is from Claudio and George from IBM, who will talk about remote attestation with Keylime. Part 3 is from Stefano and Oliver from Red Hat, who will talk about SVSM-based remote attestation. And part 4 is from Ralph from Amazon, who will talk about running Coconut on AWS bare metal instances. So let's get started with the introduction and the overview. So what is COCONUT-SVSM? The very short answer is that COCONUT-SVSM is a platform for providing secure hypervisor services to confidential virtual machines. It targets virtualization-based, hardware-trusted execution environments and is implemented currently for AMD SUSE. But support for other hardware-trusted execution environments is planned, like Intel TDX or ARM CCA. The project is written in Rust, and services actually execute in user mode for isolation reasons. The project was published last year at the OC3 conference, so it's public for 1 year now. It is licensed under MIT, and something which is very great is that it gained a broad community of contributors since its publication. So we have over 20 contributors now from many companies, and that's something really cool. Where does the SVSM fit into the virtualization stack, into the confidential virtualization stack? As you can see here, COCONUT-SVSM runs within the trusted execution environment. It runs there together with the operating system. For this setup to be secure, it needs another hardware feature that gives us memory separation within the SVSMP trusted execution environment. And that feature is called VM privilege levels. So COCONUT-SVSM runs on the highest privilege level and can isolate itself from the operating system, so that the operating system has no access to any SVSM memory. And this way, all SVSM memory is secure from the untrusted hypervisor. It is encrypted in memory, integrity protected, and also protected from the operating system running within the trusted execution environment. What are example services that the SVSM can and will provide? The most important one and the most requested one is a virtual TPM device for the confidential virtual machine. But also a UEFI variable store is a service that would enable secure boot, a migration helper for enabling live migration, APIC emulation and IRQ delivery, so that the operating system does not need to trust the host hypervisor for IRQ delivery. And also VC handling is an important service that the SVSM can provide, moving VC handling out of the operating system to the SVSM. What did we achieve in the last year? So since this publication, there were quite a lot of changes in the SVSM codebase. The SVSM gained a memory file system. The SVSM gained a virtual memory manager. It gained task support, so we can now execute kernel tasks and switch between them. The SVSM got a new boot protocol based on the IGVM file format. It got an SNP attestation report driver, so the SVSM can request an attestation report from the security processor. And besides that, many other improvements that are just too many to be named here. But that is not all. What are our plans for this year? The most important goal is to getting user mode support ready and merging the VTPM emulation support. With this, the SVSM will actually become useful. Based on that, we want to make our first public release. And as a project, we also want to join the Confidential Computing Consortium, which is already quite underway, but not yet finished. That's something we want to get finished as soon as possible. so that COCONUT-SVSM is an official confidential computing consortium project. And last but not least, we want to extend our support for hypervisors. Currently, the SVSM runs mainly on KVM, but support for Hyper-V is underway, and hopefully more hypervisors will gain support for running the SVSM. So this was the very short introduction to COCONUT-SVSM. Now on to the next part by Claudio and George about remote attestation with Keylime.
All right. Hi, everybody. Let's talk about remote attestation of AMD confidential VMs using Keylime. I'm Claudio Carvahlo, and I have worked on a virtual TPM for the COCONUT-SVSM. George Almasi and Angelo Rocco, also from IBM, they worked on the Keylime part, adding changes to Keylime to attest a AMD confidential VM. A TPM-based attestation of confidential VMs. At this point, I think we can say that attestation is a valuable feature for confidential computing. Before copying or delivering any secrets to the confidential VM, we can use attestation to check if the confidential VM is the right one and also if it's in the right state. The Trusted Platform Module, or TPM, is an industry standard and it provides crypto functions. The physical TPM has been used as root of trust for attestation. What if we have a virtual TPM that could be used in a confidential VM? Well, that would enable the existing TPM ecosystem, and we could reuse the TPM, for example, the TPM tools, the UEFI code, and also the kernel integrity measurement architecture. And with that, we would be able to do TPM-based attestation of confidential VMs. We should be able to attest the entire lifetime of the confidential VM, starting from its initial state, represented by the launch measurement, the boot measurements, attest the boot measurements, and also do runtime attestation by attesting the IMO runtime measurements. There are some challenges that need to be addressed in order to have a TPM-based attestation of CVMs. The first one is that we need to protect the VTPM state from unauthorized access. Neither the hypervisor nor the software running inside of the confidential VM should have direct access to the VTPM state. For example, the VTPM keys and the VTPM memory. The second challenge is about the VTPM root of trust. In a physical TPM, the TPM endorsement key, the AK, is signed by the manufacturer, and we can use that to check the authenticity of the EK of the TPM by checking if the EK certificate was signed by the manufacturer we expect. But here we have a virtual TPM. There is no manufacturer. We need to find other ways to still use the VTPM as a root of trust. We'll get back to those challenges in a bit. Let's talk about the virtual TPM we have developed for the COCONUT-SVSM. To address the first challenge, we run the VTPM inside of the confidential VM, and with that the hypervisor don't have access to the VTPM state because the CVM memory is encrypted. And we also run the VTPM inside of the SVSM. The SVSM is a firmware that starts at early boot and it runs with the highest privilege level, the VM privilege level 0, and code running in other VMPL levels don't have access to the code running in VMPL 0, so the VTPM state is protected. With that, we have similar security guarantees compared to a physical TPM. As a backend, the VTPM runs the Microsoft TPM 2.0 reference implementation. The TPM drivers need to be enlightened. they need to send the TPM commands to the SVSM now. The VTPM and attestation communications are encrypted, and you can find more information about that in the SVSM spec. The VTPM currently it has an ephemeral state. In other words, the VTPM, we run the VTPM manufacture procedure on every boot, and with that, the VTPM is a brand new VTPM on every boot, with new seeds and new keys. There are some advantages with this approach. It has a simple design, and the VTPM state does not need to leave the VTPM, so we can say that it has a smaller attack surface compared to other approaches where the VTPM state needs to be stored outside of the VTPM or even outside of the confidential VM. And this approach also allows remote attestation, which is one of our focus here. To address the second challenge, I mentioned that the VTPM doesn't have a manufacturer to sign the EK, but we can have the EK signed by the AMD secure processor through the attestation report mechanism. An attestation report, when we call the SVSM to request an attestation report, the SVSM will request a VMPL0 attestation report, and it will also request an attestation report that includes a SHA-512 hash that covers the VTPM EK pub. And with that attestation report will be associated with this guest, and it can be used to prove the identity of this guest and also prove the identity of the VTPM running in this guest, because the SVSM is the only one that can request this VMPL0 attestation report. Okay, if we can, depending on the use case, we can use other approaches, and Oliver and Stefano will discuss more about the persistent VTPM state later. For the development status, the SVSM, in the SVSM, the support we need to request an attestation report to the AMD secure processor is already merged. The virtual TPM and also its runtime protocol used to talk to the drivers, they are submitted. And the attestation runtime protocol that is used to talk to the attestation agents, that can be used to talk to the attestation agents, is implemented and it will be submitted soon. The Enlightened TPM drivers for OVMF and the guest OS kernel, we have an RFC submitted for them, and the keylime code need to be submitted as well. For the demo, we'll use a proof of concept code developed some time ago, but it uses a similar idea compared to the code we are using upstream in the COCONUT-SVSM. You can find the code here in these links. To attest an AMD confidential VM using keylime, you're going to need the keylime register, the keylime verifier installed somewhere, and we'll need a confidential AMD confidential VM with the VTPM enabled, running in the SVSM, and in this case it's going to be an ephemeral VTPM. And we also need the keylime, and it runs keylime agent, and it runs from user space, and it starts the process to register the confidential guest, and also later the keylime verifier do the attestation. So the first step in the demo is to set up keylime. So we're going to provide this operator configuration that shows where to find the image for the keylime registrar and the keylime verifier. In the step 2, we register the confidential VM. So we start the confidential VM with a VTPM enabled, and then once the VM is running, we start the Climb agent, which will request a VMPL 0 attestation report and verify if it was signed by the AMD key, and it will also use the VMPL 0 attestation report to check the authenticity of the VTPM EK. If the VTPM EK that we get matches with the hash that represents the EK. In the step 3, we start the Climb verifier, and it will retrieve the computational VM measurements and test those measurements against the policy. And the policy represents the state we trust, the state of the gas that we trust. And if this test fails, it means that the gas is not in the state we expect. The verifier will then do this attestation challenge periodically, and it will stop only if the attestation challenge fails. Okay, let's go for the demo. Step 1, we set up Climb. We install the verifier and also the registrar using the operator. And we see that they are running, their pods are running. And now we just check the logs of the registrar and the verifier to see if everything's okay, and we keep them open. So nothing registered so far in the registrar, and the verifier, no activity in the verifier, so as expected. Step 2, we run the confidential VM with a VTPM enabled, and it has an ephemeral state, so we do this on every boot. We can see that the VM is booting with the OVMF is doing some PCR extend, is recording the boot measurements. So confidential VM is running. It has an SVSM and also the ephemeral VTPM, and we can see that the TPM device was created, and we start the Climb agent so that the Climb agent can, and we need to provide the address of the registrar to the Climb agent, and the Climb agent will check the identity of the attestation report, if it was signed by AMD, and also the authenticity of the VTPM that is running, if it's the same VTPM that was at boot, created at boot, started at boot. And now we start the step 3, we start the verifier, but first we just check if the registrar has our confidential VM. We load the policy and the verifier. We start the verifier to check to retrieve the current confidential VM measurements and check them, test them against the policy. And the verifier will stop running these attestation challenges only if the attestation challenge fails. And it will do that, here in this case, it will do that on every 2 seconds. Okay, that concludes the demo and the VTPM part. Thank you.
Thanks, Claudio. Thanks, George. Now on to the next part from Stefano and Oliver, who will talk about SVSM-based remote attestation.
Yes, Stefan from Red Hat, and in this part we will talk about SVSM-based remote attestation. I'll let Oliver to introduce that.
Yeah, hi. In the previous part of the talk, we already heard what the SVSM is and how a virtual TPM provided by the SVSM can be used in guest attestation. And we want to talk about a slightly different approach to that. Before we start, let's look at the rough structure of an SNP and SVSM guest. So there are roughly 4 components. The first one is the SVSM, which is launched first. And in turn, then starts the OVMF, the UEFI firmware. Both of these together is the firmware package, and this is what is included in the SNP launch measurement and what is covered by the SNP attestation report. The other half is the actual guest disk image, which consists of the Linux kernel and init.ide file system in form of unified kernel image, and the encrypted root volume containing the user space programs and the actual workload. Under SEV SNP, the remote attestation has to run from inside the guest. This could, in principle, happen in any of these components. And we are proposing to do it in the early boot process from inside the SVSM. Our goal is to take the tasks away from the operating system to keep it as generic as possible. This has some advantages. So we are not introducing extra code paths in the boot flow compared to conventional virtual machines and bare metal systems. The guest OS then doesn't have to be aware that it's running in a confidential environment. This means less development and testing effort and opens the possibility of designing a single image for many virtual machine use cases. The SVSM and OVMF firmware are covered by the launch measurement. After the attestation step, we know that we can trust these and that we're running in a confidential environment. But it doesn't include anything from the disk image. And to bridge that gap, we can use existing technologies, measured boot using the virtual TPM device and secure boot. Both of these technologies are well established and are used in many systems and are well supported. We already heard that the SVSM will soon gain a virtual TPM device, and we can use this to perform measured boot. That means everything that is launched during the boot process is recorded in the platform configuration registers. These values can then later be used to identify if the system is in the correct state. And we can seal the encryption key for the root volume to this PCR configuration. This way, the disk automatically unlocks when the system boots up and is in the correct state. There are tools already available today that do this. For example, the LUX disk encryption in combination with system decrypt and roll. This key sealing does not only include the PCR state, but also the identity of the TPM. This is important so that an attacker can't just steal the disk image and use a compromised TPM to unlock the disk. The TPM that is currently being developed for the SVSM is ephemeral, which means that it loses its identity on every reboot. So this disk sealing wouldn't work with that. To fix it, we would require a persistent storage for the SVSM where the VTPM state can be stored across reboots. Secure boot is implemented by the UEFI firmware, and it requires a secure UEFI variable storage where the secure boot certificates can be stored. This store has to be protected from the host and from the guest. From the host because it's not trusted anyway, and from the guest because an attacker from in the guest should not be able to replace these certificates. On conventional x86 machines, and system management mode is used to control the access to that storage. But system management mode is not available in SMP virtual machines, so we need to do something else. A secure AFE storage can be provided by the SVSM, since it is isolated by the host and the guest. But also for this, we need persistent storage that is available for the SVSM. So the idea is that we just add a little storage device to the machine, which is then used by the SVSM. And yeah, the SVSM needs to encrypt that storage so that the host can't read it, because in the end, the underlying disk file will be on the host. The key for this encryption will be delivered by the attestation server after the attestation report is verified. The SVSM then can load the state back into the VTPM and also populate the AFE storage. Yeah, at this point, I hand over to Stefano.
Thank you, Oliver, for the great introduction. Now let's take a better look into implementation details. In this picture, we have our current status. We developed a working proof of concept based on the great work that the COCONUT community is doing with SVSM and OVMF. And we are also using the attestation report feature that Claudio developed for SVSM and that we merge in SVSM. And on top of those, we are developing the remote attestation support in order to talk with the attestation server and receive a secret. We still don't have the UEFI variable service and the stateful VTPM. So in order to use the secret for now, we are reusing the AFE secrets area developed for Save AS, and in order to inject the secret into the guest OS and then unlock the root file system. Now, let's go deeper into the remote attestation support. The first things we need to do is to do a resource registration into the attestation server. So we need to register our resource, our secret, that in our proof of concept is a Lux key of the root file system. But we need to register together with an expected SMP launch measurement, because the attestation server will release the secret only if the attestation report contains exactly the expected launch measurement. So to do that, we need the tool to do the pre-calculation. And Oliver extended the SAVSMP measure tool from the VRT community and added a new SMP SVSM mode that we can use to pre-calculate the SMP launch measurement when we use SVSM and UEFI for our confidential VM. The remote server, the attestation server we are using, is based on the remote attestation procedures defined by the RFC 9334, and the server is implementing the relying party role, and providing remote attestation and secret delivery. In the picture, we have an example of one of the implementation available. In this case, we have the CocoK broker service, KBS. And we have three phases. The first one is the authentication. So the client asks for the authentication, and the server sends back a session ID that will be stored into a cookie, and some freshness that will be used in the next phase to avoid replay attacks. So the second phase is the remote attestation, where the client will produce an attestation report and will send it to the server together with a public key that will be used in the next phase for the secret delivery. In order to avoid man-in-the-middle attacks and replay attacks, the client needs to put into the report data of the attestation report a hash of the nonce received during the authentication and the public key. In this way, if the attestation report contains the expected launch measurement, KBS can be sure, the server can be sure is talking with the right SVSM and can deliver the secret during the next phase. So the last phase is the secret delivery, where the attestation client can ask resources to the server, and every resources will be sent from the server to the client, encrypted with the public key that the client sent to the server during the remote attestation. We have several implementations for the server side and also for the client side, but for our use case, we need a library that supports no standard and no STD, Rust no STD, because in SVSM, we don't have any Rust standard library available. So for this reason, we developed a new library, Array Clients, where we support multiple servers. And for now, we support Kbroker and reference KBS. One of the main issues we had was the communication with the remote server, because in SVSM, we don't have any network stack available. So what we did, we implemented a HTTPS proxy running into the host that will forward all the requests coming from SVSM to the attestation server and send back the response coming from the server to SVSM. The guest-to-host communication, we implemented the guest-to-host communication using a simple serial port, but in the future, we may use VirtIO devices like VirtIO VSOC or VirtIO serial. This proxy, of course, is exactly a man in the middle, but we are protected by KBS protocol, as we saw using the nuance and the attestation report. The server can be sure that the one is talking with him is the right SVSM, checking the launch measurement. So at this point, we are able to receive the secret from the server, and KBS will release it only if the attestation is successful. And what we can do now is we need a way to inject that secret into the guest OS. Since we still don't have the VTPM, for now we are reusing the AP secret module. And this mechanism was originally developed for Save As, where the guest owner sent to the hypervisor, to the host, a secret page encrypted with the key, and then the hypervisor injected that page into the guest memory. We are not doing this phase, so we are just allocating the page into SVSM. So we are already inside the guest OS, so we don't need to encrypt it. But we are populating in exactly the same way, using the same UID. So OVMF and Linux will work without changes with this configuration. So at this point, what we need to do is just configure the ATC crypt tab to allow systemd to get the key from the sysfs entry populated by AP secrets and use that key to unlock the root file system and mount it. We have a demo with all these steps together, but we don't have time to show it. So we put everything together into this repo, where you can find several scripts to build your confidential VMs, pre-calculate the launch measurement, and then start the confidential VM and see how unlock the root file system. There is also a video inside the repo where you can see all the steps. So next steps. In these slides, we have our final picture that Oliver already described. So where we want to go is to support a stateful VTPM. So we will work on it. Maybe our first steps will be to download the blob state of the VTPM directly from KBS, but this will be only an intermediate state. Our final goal is to have some kind of SVSM storage support that we can also reuse to implement the UEFI variable storage service. In the meantime, we are also working on extending the SevSMP measure tool to support the IGVM launch protocol, because this will be the default protocol used by QEMU to launch SVSM. That's all for us, and thank you, and let's pass the ball to Ralph.
Thanks, Stefano. Thanks, Oliver. Now on to the next part, where Ralph will show us how to run Coconut on AWS bare metal instances.
Hello and welcome to this part of the session. Now we will be talking about running the Coconut SVSM on top of Amazon EC2 bare metal instances. I'm Ralph Waldenmaier. I'm a Senior Solutions Architect with AWS. So what is this session all about? Last year, Jörg and myself, we sat together and thought, can we run COCONUT-SVSM on top of AWS? The good news is absolutely this is possible, and in this session I'm going to show you how you can do the same. There are a few prerequisites that must be met in order to get there. First and foremost, we need to have an environment where we have full access to AMD SEV-SMP functionality. In our case, this will be an EC2 instance. Second, we need to have a Linux kernel that supports running as an SEV-SMP enabled host. Before we get into the actual implementation, let's first understand how to run compute-based workloads in AWS. We are always talking about instances and instance types. An instance is a virtual machine. Our customers can choose out of over 750 instance types for virtually every workload. In our specific case, we want to focus on an instance family that is providing the AMD CPU that supports our SEV-SMP requirements. Let's get a bit more specific. In 2017, we have launched the AWS Nitro system, a unique architecture that restricts any operator access to customer data. This is the best place for our customers to run their confidential compute workloads. What you can see here is a high-level overview of the AWS Nitro system. So for our case, because we require an AMD SEV-enabled CPU, we have chosen the instance family C6A. If we want to now instantiate such an instance on top of an EC2 host, we would implicitly ask the EC2 control plane to invoke that for us. It will communicate with the Nitro controller that on our behalf will instruct the hypervisor to do so. As our customers require fast network access and also storage access, we have purpose-built hardware for that. That is the Nitro cards. Those are attached via PCI Express to the EC2 host. One additional detail over here. We have the Nitro security chip that provides access to devices such as the BIOS flash chip. This will be important later on, as we will see in a second. Though, can we now run COCONUT-enabled guests on top of the EC2 hosts? The answer is no, because the hypervisor would prevent access to the AMD specific features that are required for that. The good news is we have a solution for that as well. Remember the prerequisites we had in the beginning, that we need to have access to all the AMD specific features that we require for running COCONUT-SVSM enabled hosts? Well, in this particular case, the architecture that you can see is a bare metal instance. The difference to the previous slide is that we no longer have a hypervisor preventing us to leverage that features. So with having that in place, we now have the hardware components in place, which fulfills one of our requirements. Let's now look into how we can actually leverage that, and I will walk you through a demo. Before we do the actual demo, let me walk you through the steps. First, we need to launch an EC2 bare metal instance, and obviously we need to connect there. Next, we are going to install a COCONUT-SVSM enabled host kernel on top of it so that we can leverage COCONUT. Third, we need to disable direct memory access. For that, we are instructing IOMMU to disable the pass-through. The AMD security chip would like to store metadata for SEV-SMP workloads. Typically, it would store that in the BIOS flash chip. Remember the Nitro security chip from the diagrams before? It would not allow writes to the BIOS flash chip. There must be another way to do so. Fortunately, there is. We can instruct the SEV-SMP system to store that metadata information on the file system. Now, this is also the next step. We need to defer loading the respective driver. The reason for that is if it would store the information on the file system too early, it would do that in the init RAMFS. Since we want to have access to the file in the user space, we need to defer the loading. This is possible with Linux 6.9 and further. The next one is we need to build our own QEMU with independent guest virtual machine support. The reason for that is COCONUT-SVSM guests will be compiled in that format. And lastly, we are going to launch an instance on top of our EC2 bare metal instance. You think enough theory? You're right. Let's dive into the actual demo. Step 1. We are in the AWS Management Console, and in order to reach our EC2 instances, we are heading to the EC2 console. I have already an instance up and running, so we navigate there. It's a C6A metal instance that we discussed previously. I just copy the public IPv4 address, and using that address, I can just simply SSH into that with the certificate that I configured. Step 2. Let's clone the Linux kernel from the SVSM project. And once we have done that, we are navigating to the respective branch. After configuring the respective kernel, we can just leverage the 192 cores in order to build it. Once we are done, we are installing the kernel. Step 3. Now we are modifying the kernel parameters to disable direct memory access. We are just appending the IOMMU equals no PT flag. Once this is saved, we are applying the configuration to the grub configuration. Step 4. Now we are going to specify that we want to store the SEV-SMP metadata on the file system. Here you can see we are providing options. For that, a new configuration file is created, and we will just verify that the configuration is in place. Step 5. Now we need to instruct that we want to defer loading the CCP driver. For that, we are creating a new configuration to omit this particular driver. Let's verify it's written successfully and then apply the configuration that we just configured. Step number 6. Let's compile QEMU with the independent guest virtual machine format support. We can obtain that from the SVSM repositories. And finally make it with our 192 vCPUs available. Step 7. Now we are going to launch a guest with SVSM support. What you can see here is the respective memory pages have been loaded in order to support that. And finally, we are having a guest that is up and running. With that, this concludes our demo where we have shown how to run Coconut-enabled guests. Now that we have seen how to run Coconut-SVSM-enabled workloads on EC2 bare metal instances, I want to emphasize on the following. With the AWS Nitro system, you have the best place to run your confidential compute workloads. Why? First of all, the Nitro architecture ensures that our operators have no access to customer data. Second, even today, you can leverage SEV-SMP features natively with EC2 virtualized instances. And for our customers that require more options, we are providing EC2 bare metal instances to support their requirements. So if you now want to learn more about the AWS Nitro system, I have provided you with the two following links. The first goes to a YouTube video from our reInvent conferences, which will explain the AWS Nitro system. The second one is our AWS Nitro white paper, which explains all of those concepts in more detail. And that, folks, concludes my part of the presentation. Thanks for joining. I'm Ralph Waldenmaier, Senior Solutions Architect with AWS.